we're going to kind of review some of the stuff about polonium halos and some of the other radioisotopic dating that we looked at last week. We talked about the three major assumptions. You have to have no contamination, you have to have conservative decay, you have to have no original daughter element. Again, this may seem logical if you're in a sterile laboratory somewhere and you've never had to dig a hole. I don't know. But we can certainly raise issues with any of the three, and my personal favorite is number 2 because that also has to do with the speed of light. So we've been over some of this stuff. Okay, one of my favorite younger creationists is Dr. Don Patton, and I've showed you some of his stuff before, but he has done a significant amount of research in this area. We're going to hear what he has to say about radioisotopic dating and some things that he's looked at. And you can find this on YouTube, Scientific Age of the Young Earth by Dr. Don Patton. I think it's also on his website. I can't remember what his website is. We'll see if our internet works for us here.
And this is the standard conclusion about how long it takes to form 1 foot of Paleozoic Leakey's best friend, editor of Research News and Science. This is the way it works. You just keep chucking until you get what you want.
We talked about this last week. Yeah.
Now, how scientific is that? This is a game that's played to verify what you already believe. If it doesn't, you chuck it and you keep playing. Let me give you some more illustrations. This is a cross-section of the Grand Canyon, and we've done some research here. I say we, myself, with several others, mainly others in this area, but we work together. As we look at this cross-section of the canyon, we can determine that some rocks ought to be older. Certainly, if the evolutionary picture is correct, the ones down at the bottom ought to be older than the ones up at the top, right? The Euencheric basalt has come out of what appear to be modern volcanoes. Some have suggested the American Indians saw these eruptions take place. They flowed over the edge of the canyon down into and damming up some of the lowest parts of the canyon. This would be the youngest rock there. Interestingly, the same type of rock is found down in the inner gorge, underneath the sedimentary layers, down in the igneous rock in the inner part of the gorge, but it's the same kind of rock, cardenous basalt, which ought to be older. Well, it's obvious which should be older. Okay, let's send these rocks to the lab and see how this works out. Well, which method will we use? There are about 20 different radiometric.
Okay, he says it's obvious, but let's just make sure we're all on the same page here. What the evolutionists would say is that this rock was laid down, right, and this is from some eruption in some eons past, right, and then tectonic forces happen, and that's why it's tilted, and at some other point, all of these sedimentary layers got laid down, and they would say that that process happened over millions and millions of years, right, especially if we're starting with Cambrian down here. The Cambrian rock is 500, 600 million years old, right? So they would say that every single one of these layers represents millions of years of time. And then up here at the top, we have a lava deposit which, erupted somewhere over there and have a nice little lava stream that's come down and flows over the top. So this is relatively recent. We call this relative dating, right? There's relative dating, there's absolute dating. So let's see if they agree. We're going to compare a radioisotope age of these two rocks and see if it agrees with the relative age of those two rocks.
Methods. But some of them would be more appropriate for this type of rock. Here we use several different methods to date the Euencheric basalt. 6 potassium argon model ages were run, and the range was from 0.01 all the way to 17 million, which is a pretty good range in itself in this one lab. The rubidium strontium came out 1270 to 1390.
That's over 1 billion years.
The lead-lead isochron, supposed to be the most accurate, came out better than 2.5 billion, which is a whole lot more than the 17 million, which was the oldest potassium argon age. Now this is the same rock. Different methods on the same rock. Now you're told over and over again that we test and the same, the different ages come out and they are concordant and they verify one another, and this is the way we check and we know it's right because they all agree. If you chuck 40 and pick the one and then you're able to do that with the others, maybe you can come out with something that looks concordant, but this is the real experience that we had. With the Cardenas basalts, let's see how that came out. Similar methods used, and again, that's all over the place, from 853 million to a billion. Huge range. Again, all from the same rock, just using different methods. But we compare...
It's kind of, you guys remember when they used to do hurricane forecasting? There would be somewhere between 4 and 12 major storms this year. It's kind of like whether we're going, I know it's somewhere between, 0.01 million years old and 2,600 million years old, right?
Yeah.
That's a pretty, you can make that rock as old as you want.
Well, we could have just guessed that ourselves.
I'm sure you already do. It's somewhere between 0.01 and 2.5 billion, right?
That's right.
And one of the things that help went now, one of the things that you didn't mention is, again, we're seeing a wide range in the potassium argon dates from about 0.8 million, so less than 1 million years old, all the way to almost a billion. So we have a tenfold, or an order of magnitude of difference between, just one dating method.
The oldest rock from the Uinkaret Plateau that flowed over the edge and dammed up the lowest part of the canyon, and it's 2.5 billion, whereas the oldest age for the oldest rock is just barely a billion. It's less than half as old as what flowed over the top of the canyon. Now, how is it that you got the lower younger? It ought to be much... There sometimes when you can test and know, at least relatively speaking, what ought to be, and when you do, I'm sorry, it doesn't work unless you do a lot of checking, which is done as we have demonstrated from the evolutionist himself. We decided to do some work at Mount St. Helens. This is a picture of the caldera. The center portion is
You're talking about this area right there.
known age. This is from 1986. The eruption was 1980, but 6 years later is where most of this was extruded. We took 5 samples from the caldera, different parts of it, and sent it to the lab. Here's the rock you dated. Tell me the age. Well, the answer came back looking like this, in millions of years. And the rock was actually 11 years old. And people would say, well, okay, it was not dating
Wow.
when the rock formed, but rock that was already mixed together as lava, and that's, of course, exactly right. The assumption of the potassium argon dating, which was being used here, is that when it flows as lava, all of the argon escapes, and when it then congeals into rock, that's when the clock starts. And you're dating the time when it became hard as rock. Sorry, it doesn't all escape. There's still plenty of argon there. It doesn't work, and gives absolutely absurd results. This is not unusual. And if you're chucking 40 out of 41, then I think you get the picture. Radiocarbon dating is the one that we hear a good deal about. It's not nearly as significant for evolution because it covers a much shorter period of time and works somewhat differently. It covers a period of less than 100,000 years, probably more like 60 to 70,000, which I think is significant when we're talking about the age of the Earth from the biblical perspective, but not the billions necessary for evolution. Robert Lee is commenting on, I think, rather objectively, the problems that have become obvious in recent years. He said the troubles of the radiocarbon dating method are undeniably deep and serious. Despite 35 years of technological refinement and better understanding, the underlying assumptions have been strongly challenged. Now, this is not just something leaks in or leaks out. This is not just contamination. The underlying assumptions have been challenged. It forms in the upper atmosphere. The assumption is that there is the same amount relative to carbon-12 that there has been for thousands of years for the time that it's being tested. We have found that's not the case. It is...
I'll just elaborate on that for a little bit. So carbon-14 is actually formed when super high energy photons hit nitrogen that's really high up in the Earth's atmosphere. So it's constantly being produced by the sun, okay? And so, you know, maybe one carbon atom out of a billion is a carbon-14. So when we look at, you know, an organism, let's say we're going to date, you know, some king of England that lived, you know, in the 1400s or something. We can do a carbon-14 date on him, assuming that the amount of carbon-14 in his body when he died is relatively close to the amount of carbon-14 that's in mine right now, right? We've discovered, looking at tree rings and dating the amount of carbon-14 in the tree rings, that the amount of carbon-14 in the atmosphere varies a lot. Solar flares and, you know, volcanic activity and all kinds of crazy things can influence how much carbon-14 there is in the Earth's environment. Just over the last 2,000 years that we've been able to look at tree ring data, we've seen a lot of variation. I've heard some people say as much as 100% variation between one, you know, carbon-14 at this time, and you move forward, and there's this amount of, so it fluctuates a lot.
So that is, the carbon-14 is increasing, it's not staying the same. Libby, in his original work, said it would only take 30,000 years to reach this state of equilibrium, and it's not there, which is interesting. But he continues saying, it should be no surprise then that fully half of the dates are rejected.
That's pretty optimistic.
That's, I think, overstating his case. He is, of course, a believer in this and uses it. I have a friend who runs the carbon dating lab at Ball State University. He's a brother. We differ on the age of the Earth. And we were discussing this, I think, in a brotherly way. And I was visiting him there at the lab, and he was dating a peat bog with the carbon-14 lab that he had, and he had chucked the first 19. He was on the 20th day. He knew it was 20,000 years old.
Oh, you know
it's
how
come out 4,000 to 5,000. Therefore, it proved that it was contaminated with recent material, so he's going to get a good one yet. He's chucked everything he's gotten so far. 19 out of 19.
Oh, jeez.
And so when he says half the dates are rejected, I think he's understating the
He probably doesn't
situation.
know.
He continues to say there are gross discrepancies, the chronology is uneven and relative, and the accepted dates are actually selected.
Aha! Well,
I submit to you, this is not science. This is a game that's being played in order to make people look like they know what they're doing, to verify prior conclusions. Even W.D. Stanfield, who is a vicious anti-creationist, writing in his book Science of Evolution, it is obvious, and this is after we had presented some of this material, that the radiometric technique may not be the absolute dating methods they claim to be. And I think that's for obvious reasons. I think one of the best ways to approach this is to look at what might be called the proof of the pudding type arguments. Let's look at situations where we should be able to tell, at least relatively. Grand Canyon would fit into that category. This is from the Glen Rose limestone, not too far from here. This is supposed to be 110 million, middle of Cretaceous. Well, a friend of mine, an associate, sent this to the UCLA carbon dating lab without being completely straightforward about where it came from. It came back dated at 890 years old, from 110 million year old limestone. About 50 yards away, there was a carbonized stick in the same layer, and so he sent some of this to the same lab. It came back dated 12,800, which is considerably more than 800 years old, but all considerably less than the 110 million. Now, if you kept sending, you might get one that they would accept, because the response would be, well, you're crazy. You don't send material for radiocarbon dating from 110 million year old limestone. It's all gone within 50, 60,000 years. Now, it should be, but guess what? It's not. We have dated over 100 dinosaur bones now with radiocarbon dating. This is the ilium bone there from Glen Rose, supposed to be 110 million years old. It came back dated 19,000, a long ways from 110 million. And in 65 million years, since the dinosaur was supposed to have been extinct, all of the carbon-14 would be gone, like in 50 or 60,000 years. And so you're crazy for even trying to date dinosaur bones. If you think it's 110 million years, yes. But I don't. And we've dated over 100, every single one of them, 100 out of 100 had significant radiocarbon in it.
Well, there you go, folks. It doesn't get much clearer than that. There's a whole lot more to this video. He goes into some laws of physics and gets into fossils that were formed quickly, and a lot of stuff that we've covered as well.
Well, it seems like carbon dating, the theory makes sense, but in reality it just doesn't.
It's just not working for them.
Mm-hmm.
You know, they would say, I mean, if the entire Earth was made out of carbon-14 atoms, all of them would decay in 1 million years. There would be none left. So trying to say that something that's supposed to be, you know, have been fossilized 110 million years ago, and here it has a significant amount of radiocarbon in it is ridiculous. And of course, I've tried to do some research and try to figure out what the evolutionists say about this, because, you know, they get hit in the face with this all the time. So surely they have some kind of an answer, and they're trying to say that it's radiogenic, that the carbon-14 is from radioactive decay from, you know, these high-energy photons. I don't know if they know this, but the rocks that these things are in are not transparent to high-energy light. You know, this is sedimentary rock, or it's not in granite where you have this kind of decay that's occurring. So they are really grasping the straws here. As far as I know, they've got nothing for all this. Carbon-14, we find some in diamonds, we find carbon-14 in all kinds of fossils and coal and oil, and it's just all over the place. All kinds of places that it should not be, even though we, again, test everything, or we treat everything with bleach and acid and remove any kind of contamination that could possibly be there. You can look this up on Answers in Genesis as well. There, you know, he mentioned that colleagues of his have done a lot of this research, and they're some of these colleagues that have been working on this. If you want the technical data there, it's all there. All right, we got a cruise. If I can get this thing to work for me. So that's carbon-14. We talked about 1470 skull. You know, it's dated at 2.61 million years old. The 41 different tests that were done on it, and none of them agree with each other. Okay, we're going to talk about this again today. Maybe figure out what we're talking about here. Polonium halos. We've talked about the fact that granite gets small little pieces of radioactive material stuck in it when it forms, and as that radioactive material decays, it leaves traces in the granite, right? And that kind of hopefully makes sense. So if you've got a solid rock and you have, you know, a gamma ray or something like that, high energy photon that's emitted from the nucleus, well, it's going to leave a trail in the rock as it passes through it. Same thing with an alpha particle. You have an alpha particle that's emitted, it's going to leave a trail through the rock as it travels through the rock. Now, we're very familiar with, you know, for example, the energy associated with alpha decay, beta decay, and gamma decay, and all these different things. And as you work your way through a decay chain, you can actually tell what the radioactive substance was that started this decay process. All right? So we talked about alpha decay demotes an isotope, right? So if you have uranium and it goes through alpha decay, it's going to turn into thorium because it's lost 2 protons. Changes the chemical nature of material. right? Beta decay similarly changes the nature of the isotope, the element that's going through beta decay. It's emitting a high energy electron, so a neutron is converting itself into a proton and spitting out the negative charge, and it's retaining the positive charge, and that changes its identity to a proton. So that promotes an element, right? So you get thorium, it's going to go through beta decay, and it's going to change it to protactinium, I think is what.
Why does it do that? It's just natural decay?
Well, it's kind of like, it's more stable that way.
All right, good.
It's kind of, and the best way I can explain it does this because of the electromagnetic force, which is not something most of us are familiar with as far as, dealing with it on a regular basis. We're all familiar with the idea that things fall downhill, right? Why do they fall downhill? They're more stable that way. They have less gravity potential energy, according to physics. If you have something that's high up, it has a lot of potential energy due to gravity, and if you release it, it's going to fall, and it's going to release that energy, and you can calculate how much energy it has, and all that stuff, for hydroelectric dams and things like that. So this decay is happening because you have an element that's not stable, and it wants to become more stable. It doesn't want it. It's falling downhill. So eventually a mountain will erode, right? Natural processes happen. You shake it. When you shake a box of sand, it's going to become more level. Right? That's what's happening here, basically. Without getting too nerdy on. Okay. And then gamma decay is another common type of decay where we don't change the identity of anything. Gamma rays are more energetic than X rays, and they're really moving fast. So when a gamma decay occurs, it's just removing energy from the nucleus. Now, there are other types of decay that happen in a nucleus. These are the three most common. Okay, so whenever this kind of decay happens over a long period of time, right? You've got a particle in the granite that is, let's see if I can get this thing for us. And a particle in the granite that is decaying over time, and so if you have this tiny little speck of uranium atoms, for example, uranium-238, and it's going through all of these different decays. Uranium decays into thorium, decays into protactinium, which actually decays back into uranium, which then decays back into thorium, and so on and so forth, through this 13-step process before it finally gets to lead-208, I think, where it's stable. Well, it's emitting all these different particles, right? And certain alpha particles are going to have more energy than other alpha particles, and all this stuff. So you're gonna actually, what you're gonna end up doing, you have all these particles zipping out from the nucleus and traveling a fixed distance through the rock, and a tiny little speck of uranium can have billions of atoms. So these things are coming out in random directions, and what you will end up creating is a little sphere that's discolored, distorted. The rock has been distorted. All right. Now, if you crack open a piece of uranium and you look at it under just a regular optical microscope, you can see this as a little halo. It looks like a little ring around this tiny little particle of some radioactive material, right? So we can look at this and say, okay, well, here's a gamma ring, and maybe that's a beta ring, and that's an alpha ring, and we can count all these things up and kind of figure out how many alpha decays and how many beta decays this thing's gone through, and therefore, okay, well, where did it start on this decay chain, headed down towards lead? Okay, this is very solid science. They've been doing this since the 60s. They published in many respected research journals, Nature and Science, and they've got a couple of those.
So there's no
One here.
holes in that.
As far as we can tell. Like any good scientist, once they found this evidence, they try to go out and disprove themselves. They've been trying to disprove themselves for 65 years, and I guess it's 55 years, since the mid-60s, mid to late 60s, and haven't found anything. They've been trying to figure out a way that you could get, this effect without
Are they more objective in this science than they are in, say, carbon dating because of the implications?
I don't honestly know.
Seem like they're
These
more
guys, these guys seem to be pretty level-headed. You know, for one thing, they're trying to disprove themselves. Most scientists who discover something are all trying to prove that it's true, right? Because they want it to be true. They're biased that way. These guys seem to be like, well, okay, we think this is true, but what if this happened? You know, what if there's a crack in the granite and you have some kind of, you know, water that transported these materials down there? You know, they're trying to be as objective as they possibly can and look for cracks in the granite and try to say, okay, well, are these halos more concentrated in one area than another? And then just, they have 20 different reports about all the different things that they've been doing to try and falsify their own claim. And so far, this is just making their case stronger and stronger and stronger. And as far as I know, nobody's ever even tried to challenge it. They just ignore it, as far as I know. But you know, I'm not the end-all expert on this stuff. Okay, so let's try to figure out what they're talking about here and why it's, you know, such a big deal to guys like me. Okay, so as we talked about last week, when uranium undergoes an alpha decay, spits out an alpha particle, it loses 2 protons, it's demoted itself. Okay, it's now less massive and it has a different chemical nature, right? It has fewer protons and therefore the way that it behaves, or its chemistry, is different, okay? With carbon-14, it's a simple process. Carbon-14 decays into nitrogen. Nitrogen is one of the most stable atoms in the universe, right? No big deal. With this stuff, it's a little bit more involved because uranium is decaying into something that's also radioactive, which is decaying into something that's also radioactive, and I'll show you what we're talking about here. We have a decay, what's called a decay chain, right? And again, the whole reason why this is happening is because you got all these positively charged particles in a very small space, right? So according to electromagnetism, those positive particles should repel each other, and that thing should explode by all the laws of electromagnetism. So there's got to be some other force that's holding this thing together, okay, and opposing the positive repulsion that these particles are feeling, right? That force that's exerting on all those protons. We call that the strong nuclear force, right? Strong nuclear force is unbelievably strong and unbelievably short range. To the point that if you build yourself a very large atom, it's not stable because you have this tug of war. On the one hand, you have the strong nuclear force trying to bind that atom together, and on the other hand, you have the electromagnetic repulsion between the protons that is trying to blow the thing into smithereens. All right? So you have a tug of war, you have an instability. We call that radioactivity. Radioactivity is the instability in that tug of war. Okay? And so over a certain period of time, a certain number of these guys will blow up in their own little way. And they'll spit out a specific particle. Right? So once half of them have blown up, we call that a half-life. Some things are more stable than others. Uranium is actually pretty stable, believe it or not. Okay, so that's spitting out an alpha particle. And again, it's increasing its stability. It's becoming less, oh good heavens. It's becoming less massive, and therefore, you know, these two guys are getting along a little bit better now that the alpha particle has been kabooted, right? Because they're better able to exchange, I think they're pions with the little particles that cause a strong nuclear force. And again, this is why we don't have atoms with 200 protons. You can create one and it'll last for a quarter of a half of a third of a billionth of a second before it blows up. It's just so unbelievably unstable that it kicks the bucket really fast. Okay. Now, one other way that they kind of get around this whole instability is to have more neutrons. Right? Like carbon has the same number of neutrons as it has protons, right? And if you add more neutrons, that actually makes it unstable because neutrons are not stable by themselves. I don't know why, they're just not. But if you have a very large nucleus, 92 protons in the uranium, but there's many more than, I think there's like 130 neutrons compared to like the 92 protons. So there's a lot more glue, if you will, trying to hold it together. Okay, anyway, we're looking for a specific little graph here. I'm gonna get through all this stuff. There's a lot of fancy math here that I do not pretend to understand. We're getting closer. Here we go. Decay chains. So, since uranium is decaying into something radioactive, let me see if I can get that a little bit clearer. Maybe. Okay, so uranium-238. 238 is the mass number. That's the sum of the protons and the neutrons in the nucleus, because where almost all the mass of the particle is in the nucleus there. All right, so it's an alpha particle. It has a half-life of 4.5 billion years. To thorium, right? Uranium nucleation of thorium. Now it's a beta particle and it promotes itself to protactinium. Now it has, so thorium has 90 protons, protactinium has 91. It's the only difference between them is the number of protons. Okay, and then it promotes itself again after the half-life of 24 days. So it's really cooking, we should say. Beta emission again, we're promoting ourselves to uranium, but this is a different isotope of uranium. Right? Now our uranium-234. Well, this will make the exact same molecules, it will have the same chemistry as the other uranium. However, it's less stable. Okay? Similar to the carbon. The carbon-12 is very stable. It's unbelievably stable. Carbon-14, not so much. Very unstable. Alright? So, this is actually what we make nuclear bombs out of. Okay? Because when we can cause it to spontaneously decay if you hit it with another particle. Right? I'll teach you a little bit of nuclear physics here. So, if you just have, uranium as it comes out of the ground, almost all uranium is uranium-238 as it comes out of the ground. Very, very, very small amount of granite is uranium, way less than 1%. But you can refine it, and you can get your uranium out of there. But most of and it looks like lead, actually, very similar, although it's much heavier, much denser, I should say. Almost all of it, almost like 99% of it is U-238. Okay? It's radioactive, it's not stable, but it's too stable to make a nuclear bomb out of. Because once one of those particles decays spontaneously, what you need, if that alpha particle or beta particle, the electron or gamma ray, hits another nucleus, it will cause that nucleus to spontaneously decay. So normally this process would take 240,000 years per half-life. But if you can get enough of this stuff together, then whenever one of them decays, it will hit another one, and that one will decay, and this one will actually emit more than one particle. That's also important when it's spontaneously decaying. And so you've got two particles, and it hits two other nuclei, and they spontaneously decay, and they hit. Now you got four particles, and then 8, and then you get the idea. A quarter of a half, a third of a second later, almost all of that material is spontaneously decaying, and you have a nuclear explosion. That's what a nuclear bomb is. Okay, all of this, I say all of it, there's some of it that doesn't go through that process, and that's why there's so much radioactive material strewn all over Kingdom Come after a nuclear explosion. Right, and up into the atmosphere, and the dust is radioactive, and the water's radioactive, it's bad. Okay? So, in order to get a nuclear bomb, what you have to do is increase the concentration of U-238, U-234, or U-235. There's also a U-235. You have to increase the concentration of that isotope in your sample to 5 or 6 or 7%. This process is called enriching uranium. You've heard of it before, right? Now you have to enrich uranium, what they call weapons grade uranium, to that 5, 6, 7%. I think it's actually 6%, 6.5, something like that. If you're going to build a nuclear bomb, otherwise the thing won't work. All right? There is no critical mass. Okay? But if you get it up to 6.5, 7%, U-235, U-234, now all you have to do is have 2 subcritical masses of U-230 of uranium, smash this one into that one, you have a critical mass now, and a quarter of a half, a third of a second later, everything blows up. Okay, and if you get really fancy, you have one mass in the middle and 3 or 4 masses around the outside and cause them all to hit the middle, now you have a very high grade, a high yield, I should say, a much more powerful bomb. Right? So you have to enrich uranium if you're going to build a nuclear warhead, and so that's why everybody with a brain understands that Iran, and they've actually admitted it now, we understand that they're enriching uranium for nuclear warheads. We know for an absolute fact that they don't need enriched uranium to have a nuclear energy program. It's just simple science. And for our politicians who had an 8th grade education, they understand that. Of course, I think they did all the whole time. I don't know. Let's not get into that. Okay, so anyway, my whole point is, these things are unstable. You guys understand my rap jokes. Okay. These things are unstable, they're decaying, so your U-238 is pretty stable, half-life of 4.5 billion years in the present. Okay. That's decaying. It has thorium-234 is much less stable. Right? It has a half-life of 24 days. And it's decaying protactinium, which is even less stable than that. That's a half-life of 1.2 minutes. Ridiculous, man. That stuff's blink and it's gone. You know, very radioactive. Okay, radium-234. All right, it's much more stable than those two, but less stable than the original uranium, right? So if we can think of this in terms that your kids can understand. Let's say we have a giant pot, a giant swimming pool sized pot of uranium-238. Okay. And it's a giant iron pot. And we have a very slow, very low amount of heat. Just a few coals down underneath it, and it's slowly evaporating. We have this little, got a lid on it, where we can collect the evaporation, and it will drip into the next pot. Okay? So it's kind of boiling, it's not really boiling even, because it's very stable, right? So it's kind of, exiting the one pot very slowly and dripping into the next pot. Well, the next pot is thorium-234. Well, it collects in that pot, but it doesn't stay there very long. It's a very small pot. It's got a lot of heat underneath it. So this guy, very short period of time, he's decaying protactinium. And this guy's just a little thimble, right? So once he gets into there, man, he's just out of there almost as soon as he gets in. And then he's falling downhill. He's decaying. Okay. Now this fourth pot over here is actually a significantly large pot and doesn't have that much heat under it, right? So it has a half-life of 240,000 years. So it's significantly more stable than these two guys, right? Okay, but it's also decaying. We're not saying that it's stable. Thorium-230 is decaying. It only has a half-life of 77,000 years. You get radium, and then you got 1.6. So you have all this little series of materials, and they're all in the same little particle. And some of those particles are protactinium, and some of them are radium, and some of them are polonium-218, and some of them are radon, and they're just kind of all falling downhill through this decay chain process. And they end up emitting like 13 alpha particles, which very quickly become helium, right? An alpha particle is just a helium nucleus looking for some electrons, right? And eventually, this whole thing decays to lead-206, which is finally stable. Thank goodness, right? We can make bullets out of it, stuff like that. Batteries, that's nice. Let's make batteries out of it. Stay fine. Okay, so this is the decay chain. We're spitting out a lot of alpha particles, right? And as soon as they get out into the rock, they're going to be helium. So we've talked about the fact that most of that helium is still in the zircon crystals where it came from, right? To the point that we think a lot of this decay, today it takes a sample of uranium 4.5 billion years for half of it to decay, right? But apparently about 1.5 billion years or so of decay has happened very quickly because we've been able to find a lot of helium still in those crystals. Right? This is indication that our assumption number 2, constant rate of decay, is not valid. Constant rate of decay in the present. Back then, it was nuts. Okay. Back where I was. Alright, so, all this decay stuff is happening. Eventually, we get this thing down to polonium-214. Now, you only thought that the protactinium was unstable, right? With a half-life of 1.2 minutes. Polonium-214 has a half-life of 160 microseconds. Okay? A microsecond is a millionth of a second. So a standard camera flash, back when cameras used to flash, is about 1,000 microseconds. And it takes you approximately 350,000 microseconds to blink. Although if you're a speed blinker, you can get that time down a lot, okay? So, if you have a pound of polonium-214 on your chemistry table, by the way, congratulations on getting that much of it all at once, you blink and it is gone. It blew up. It's now all decayed into whatever's the next step down, okay? So this is a very unstable, extremely radioactive material, okay? Unfortunately for the evolutionists, we have found halos in granite that definitely started as polonium-214. Not uranium-238, which is what we would expect to find. We would expect all these halos to have started at uranium-238, and maybe the occasional one as uranium-234 or something like that, right? Yeah, we find that have definitely started as polonium-214, which should not be possible, okay? For a couple of reasons, 2 reasons. Okay, so that should not be possible. I'm going to talk about all that stuff. The issue with polonium-214 halos is granite is assumed to have formed slowly and cooled slowly over millions of years worth of time, all right? So finding a halo made by something that has a half-life 2,000 times shorter than the blink of an eye is kind of like saying that in one instant all of this granite was molten and then the next instant, I'm talking about a microsecond here, okay? The next instant it was all solid, which is perfect nonsense. All right? Because again, they have to believe that this stuff cooled over millions of years. The reason being is it's made of 3 different things that all have different melting points. Yeah, that's not, in chemistry, in organic chemistry, one of the things that you do is distillations, where you separate things out based upon their boiling point. I do the same thing when I smelt lead. I don't smelt it. I melt it back down and get all the steel and stuff out of it. So that's one of the things that I do is I'm working with things that have different melting points. So I'm constantly babysitting, my little lead pot and fishing out anything that doesn't melt in there because it's no good. It's either steel or zinc, usually. So I'm separating out based upon its melting point. And since lead is denser than all that other stuff, it just sinks to the bottom and like little bolts and nuts will float right on top of it and be like, ha. So that should happen with the Earth's crust too. If it cooled quickly, you'd have a separation. You'd have distinct layers of mica, feldspar, and quartz. You don't have that. You have everything all mixed together. If you melt granite down and let it cool, it will not form back into granite. That's what I'm trying to say. All right? So even if it were possible for everything to cool instantaneously, we still have the issue of decay chains. All right? In other words, if you find a little piece of this chain, if you find that little polonium-214 there, why, he's got a whole bunch of fathers and grandfathers that should also be present in that same little particle. Because remember, as this trickle effect is happening, we still have a lot of uranium-238 that hasn't even decayed yet, and won't for billions of years, right? So it should be absolutely impossible to have pure polonium in your granite. Should not be possible. All right? It's almost like, I mean, if you're going to have, and again, this is just for silliness here, if you have something that's decaying into thorium, and the thorium is a much smaller pot, and it's overflowing very quickly into the protactinium, which is even tinier, and then the uranium-214 or 234, which is larger, more stable. So we might expect to find a few halos that are like this, but most of them should be this guy right here. Right? We should not be able to find. I mean, for heaven's sake, the polonium-214 is not even a pixel. on this scale, right? He should have all of this other stuff with him. All of these particles are in the same, all these atoms, I should say, are in the same particle in that granite. It's almost like, I mean, if you were going to actually duplicate this process, what you would have to do is instantaneously create the entire Earth's crust. One instant it's not there, the next instant it's there. And you would have to specially create de novo from nothing all the various atoms that make up the Earth's crust. So one instant, 1 microsecond, there's no Earth's crust. The next microsecond, there's all this Earth crust everywhere, and you've got little particles of polonium-214, just the same as you have little particles of uranium and all this other stuff that's running around. And a blink of an eye later, there's no polonium-214 because it's all decayed. And they've been sitting there these thousands of years just waiting for us to discover them. As far as I know, the evolutionists have no answer for this polonium halo business, which is why none of you ever heard of it until you took my class. Well, they heard of it last year. Okay? Again, getting back to this, feldspar has a melting point anywhere from 600 to 1200 Celsius. Quartz is way up there, 1700 Celsius. Mica, approximately 1250 Celsius. And you can check it all out. There's lots of good technical stuff on here, and I'll be honest with you, some of it goes over my head. But I can figure out kind of what they're saying. And they're like, yeah, so it's basically 1 microsecond, no Earth's crust. Next microsecond, all the Earth's crust. You have to create the polonium-214 from nothing in place. And then it's gone in the blink of an eye. Literally. Actually, a lot less than the blink of an eye. It's all gone. And it makes this little halo. And it's just got this little footprint left behind that we can detect. And we've known about this since the 60s. And these guys have published dozens of papers about all the different tests they tried to do and try to explain these polonium halos in any other way, and they can't do it, and nobody is even challenging them. They published in Nature, they published in Science, they published in creation journals for decades. So, I think that's a pretty good argument for a young Earth and an inconsistent radioactive decay rate. Right? You had a lot of radioactive decay in the past, generated all these alpha particles, made all this helium, which is still in those crystals. Yeah, a lot of it, 50% or so of the helium is still there. Okay, you guys ever heard about the shrinking sun? We're going to move on here. When I say shrinking sun, you say, what? Well, I haven't been out to measure it, okay, recently. And I don't think I have a measuring tape that long.
Should we stare at it?
Yeah, that's probably not, even staring at it through the Earth's atmosphere is a bad idea, okay? But there was a time in science that folks believed that the sun got most of its energy from shrinking. It was well known at that time, 200 years ago, that if you compress something, it heats up. And if you compress a gas, it heats up, like on your compressor. A lot of that heat comes from taking a certain amount of gas, compress it, now you're concentrating all this energy into a smaller space, therefore the temperature goes up, right? So people say, well, if the sun shrinks, if it compresses due to gravity at a certain rate, then it heats up. And it could actually heat up at the same rate that it's spitting out energy in the form of light. So maybe that's where the sun gets its energy from. Before nuclear physics and all that stuff was even dreamed of, this is how scientists explain where the sun got its energy. And they even calculated up how much it would have to compress in order to make a certain amount of energy, and they had it all worked out, and the sun would lose a couple of feet every second, right, of its diameter. Okay. Now, this article was published in 1980. That's longer ago for some of us than others. Many years before, or I should say several years before I was born. So they used to believe, scientists used to believe, that the sun was shrinking approximately 0.1% per century, a shrinkage rate of approximately 5 feet per hour. Wow. It's making a lot of energy. Well, I should say it's concentrating its energy, right? The data that they had examined spanned a 400-year period of solar observation and confirmed that the sun is apparently shrinking over that 400-year process. Which I think is interesting because I also think it's very possible the sun gets its energy from nuclear fusion, just like mainstream science. So, again, I don't know. I wasn't there when the sun was made, and God didn't consult me about, how should we power this thing? We could just make it shrink a little bit, and that'll be fine, or we could do this fusion thing, which is really cool. We could do both. I don't know. I have no idea. All right. So if you calculate yourself backwards in time, if you have a constant rate of shrinkage, 2.5 feet per hour of your radius is disappearing, so you go back in time, 100,000 years or so, and the sun and the earth are touching, and all that stuff. I think there's a little, there you go, something like that. It swallows up the orbits of Venus and Mercury, that's a pretty bad sunburn, I would say. You're getting into the corona. Corona is the unbelievably high temperature. So 100,000 years again is a very long period of time. You start talking about, biblical age of the Earth. Actually, I think it's more like 1 million years. 100,000 years, I think, is like twice the size of it is now. Right? That's probably more like. You can read about it if you want. Let's see, 100,000. Yeah, there you go. 100,000 years ago, the sun would be twice the size it is now. Let's say pretty altered conditions, again, possibly more solar flares, who knows what other effects you might have happen. Timescales for evolution range from 500 million to 2 billion years for life to have evolved, right? Yeah. So anyway, that's kind of old argument, right? Nobody talks about it anymore. I think it's interesting, so I'm going to bring it up. These days, scientists don't think that the sun gets its energy from shrinking, and there's actually a considerable amount of debate about whether it is actually shrinking or not. Go figure. Most people think that the sun gets its energy from nuclear fusion. Now, what we've been talking about so far is called nuclear fission, not like fishing, but fission, where you take a large thing and you break it up into smaller things. Break it up into, you're dividing it, right? So that's taking a very, very large molecule, or atom, I'm sorry, and breaking it up into smaller pieces. That's what we use our nuclear bombs. That's what a nuclear bomb is. That's what nuclear energy gets its energy source from. There's another type of nuclear energy. You guys are probably familiar with something called a hydrogen bomb, right? And also this idea that hydrogen bombs are much more powerful than your standard everyday garden variety nuclear warhead, right? What's the big deal with hydrogen bombs? Well, if you can compress hydrogen at unbelievable high pressures and ridiculous amounts of gravity or temperature, you can actually smash two hydrogen atoms together so hard that you will overcome the electromagnetic repulsion between those two protons, and you will make yourself a helium. Okay, that's fusion. You're taking two smaller atoms and you're making yourself a larger one. This process also, similar to fission, converts a small amount of matter into energy. All right. So, but this is a much more efficient process than fission is, and there's no nuclear, radioactive decay that's left over either. So that's what a plasma reactor is. A plasma reactor is taking helium and heating it up to 100 million degrees, and basically that translates into those atoms are moving around at like 90% the speed of light, man. And when they smash into each other, they make helium, and you get an unbelievable amount of energy out of that reaction. It'd be really great if we could make these things efficient and actually get more energy out of them than we put into them. We can't do it yet. Maybe we will one day. I don't know. Science is divided on the subject, but the sun apparently does this all the time. Very difficult to do on the surface of the Earth. You have to get those particles up to a very high speed to smash them together and overcome all the electrical repulsion between those protons, so the strong nuclear force can take over once it gets close range and you can make yourself a helium, right? But if you got something like the core of the sun handy, what? That's a perfect environment. I mean, you're talking about a lot of gravity, a lot of heat. Oh, you are really good at taking hydrogen, smashing it together, making helium, and in the process releasing gobs of energy, right? So, most people think that's where the sun gets its energy from. However, there's a problem with that. Because as you're turning your hydrogen into helium, what's happening? Well, we don't think of helium as being very dense, do we? But it's much denser than hydrogen is. Right? It has a lot more mass. Well, things that have more mass per atom are denser. Right? So a specific number of atoms, or a specific amount of space, has more stuff in it, and therefore more gravity. Okay? So as this process is going on in the core of the sun, there's more and more helium down there, and therefore the sun is getting denser over time. Does that make sense? We're taking all this stuff, we're smashing it together, and the volume of the sun is decreasing relative to its mass. Okay? Translation, you have an even better furnace in the middle of your star to turn hydrogen into helium. Does that make sense? Because the gravity was half the battle anyway, right? If we have more gravity because we're getting a denser star, then this process is speeding up. And we now have a better furnace, and we're releasing more energy, and we have a higher temperature. And this, again, fuels a faster fusion process. So this is a feedback mechanism, right? It's going to, the sun's energy output is going to increase by a lot until you start running out of hydrogen in the sun's core. When that happens, it'll start getting dimmer and dimmer, and the sun will eventually burn out in, 5 billion years. I don't plan on sticking around. You can watch it burn out if you want to, but I'm not going to be doing that. Okay. Now, this is not a problem for us. We don't care. In 6,000 years, there's almost no difference. But if you want to talk about millions of years, now you got a little bit of what we might call a problem. Because as you work yourself backwards in time, the sun is getting less dense, and you have less of a good furnace in the core of the sun. You have less helium down there, and therefore we have ourselves the young, faint sun paradox. Okay? So what we're saying is, if you want yourself a billion-year-old universe, or heaven forbid, a 4.5 billion-year-old solar system, at the beginning of it all, you're going to have yourself a very dim sun. It's not going to be very bright. Okay? And so unfortunately, it's not going to put out nearly as much energy, and you're going to have yourself a giant frozen snowball instead of the Earth, right? And he gives a lot of it. One of the things I really like about Institute for Creation Research and Answers in Genesis, they'll give you all the introduction and information that you need. So you'll hear this, you'll be like, hey, that's pretty cool. You'll forget it. But you can go back and read it, be like, oh yeah, I remember when he talked about that. So yeah, talking about nuclear fusion, he's talking about all this stuff. Great balance. Okay, so supposedly, the sun has been a main sequence star since its formation, 4.5 billion years ago. Time represents about half of the 10 billion year lifetime of the sun. And so if you're going to assume that this is main sequence and we're going to go back in time, you're going to get yourself approximately 40% increase in solar luminosity. It's 40% brighter today than it was 4 billion years ago, give or take. Now, all of these scientists are running around terrified about a, 0.2% increase in CO2 on the surface of the Earth, right? Imagine if we tried to throw around a 40% difference in luminosity. I'm moving to Venus. I don't know about you guys. We're going to make Venus a habitable planet here. That is ridiculous. 40% change should have produced dramatic climatic changes comparable to the differences currently between Venus, Mars, and the Earth. We're talking about mucho grande differentiate, right? Pardon my attempt at okay. So approximately 4 billion years ago is supposed to be about the same time that life is evolving. Now, scientists disagree about this. Sometimes they say 2 billion years ago that life is evolving. But suffice it to say, they require that the Earth have a full ocean this whole time, and all of the chemistry that's going on in the ocean, it's slowly, life is evolving. They're all requiring that. So you have to have an almost constant temperature on the surface of the Earth for this to happen, which requires an almost constant luminosity from the sun, and hence the paradox. Okay? So we could say, well, the Earth started out cooler than it is today. It's been slowly warming over time. Not really an option. You look at the rock record, that insists that the Earth's average temperature really hasn't varied much over the entire history of life. Interesting. So, and again, biologists are requiring a nearly constant average temperature for the development and evolution of life. How do you resolve this paradox? Why haven't you heard about it before today? Okay, so it's usually argued that our early atmosphere was different than the one we have today, and which is perfect nonsense. I can probably prove that, but anyway, so they say, well, the early atmospheres were different. They're called primary atmospheres. You got hydrogen running around everywhere. Okay, unfortunately for them, they need that kind of an atmosphere to supposedly evolve life, a reducing atmosphere, because oxygen will kill anything. You guys know oxygen is toxic? No, not really, but yeah, it's not that toxic, but you go blow a bunch of oxygen on a bacteria, it'll kill it. So the same things that you would need, so they argue that the first bacteria to evolve were anaerobic and didn't use oxygen, right? And then slowly over billions of years you have finally photosynthetic bacteria evolve, and they produce oxygen as waste. And that's where all the oxygen in the Earth's atmosphere came from, right? So they have to have this argument for a reducing atmosphere back in the past. Unfortunately, it doesn't hold heat very well. And this is the same time period that they absolutely, according to their own time scale of stellar evolution, would have a 40% dimmer sun. Yeah, this is not looking good for them. So you got less liquid water, they respond to a runaway greenhouse effect. It happened on Venus. On Earth, CO2 easily dissolves in water and precipitates out to form carbonate rocks. So we got lots of carbon on this planet. Most of it's in the rocks, though. Okay. Our geologically active surface is using plate tectonics to recycle CO2 back in the atmosphere, which I have some serious problems with plate tectonics. But anyway, so you got less liquid water on Venus. So removal of CO2 from the Venetian atmosphere is impossible, and hence you can melt lead on the surface of Venus. Lead is a liquid, as is gallium and germanium and tin and arsenic and a whole host of other metals that are liquids on the surface of Venus. As a matter of fact, we think there's a precipitation cycle on Venus based on metals instead of water. It actually snows or precipitates like metal, like on the mountaintops, they reflect radar energy better than the valleys. I'm like, what is going on? Oh, hey, it's really hot over there. Anyway, yeah, we're not sure about that. I've never been. Don't plan on going anytime soon. So Mars has lots of CO2 in its atmosphere as a percentage of its atmosphere. It's very, very thin. It's like 10,000 times weaker than the Earth's atmosphere, and so no appreciable greenhouse effect. So most of our CO2 has been locked up in our surface rocks, right? So we're supposed to have this atmosphere that's evolving, okay, according to evolution. They have to have an evolving atmosphere, and therefore our current atmosphere is a secondary atmosphere. Okay, that's my point. All right. So let's see. Early life forms are supposed to have introduced free oxygen into the air, O2, and regulated the amount of other gases such as nitrogen. Living things need nitrogen, right? Nitrogen fixation and all that jazz. As new life forms evolved, supposedly, the mix of gases in the Earth's atmosphere gradually changed. Evolution proposes that the early atmosphere contained a greater amount of greenhouse gases, such as methane, than today, This would have produced average temperatures close to that today, even with a much fainter sun. As the sun gradually increased in luminosity, the Earth's atmosphere is supposed to have evolved along with it, so that the amount of greenhouse gases have decreased to compensate for increasing solar luminosity. Really? Well, isn't that just peachy? Wow. Okay, so the precise tuning of this alleged co-evolution is nothing short of miraculous. Mechanism driving would have been a complex system of negative feedback working very gradually. It's not at all. I mean, they don't even have an idea for how that could work. So we can't even make fun of them for having a stupid idea about how negative feedback could work because they haven't even thought of it, because it's probably impossible. Anyway, even by their standards. At any point, a slight positive feedback would have completely disrupted the whole system, and you either get Mars or Venus. Ugh. Current makeup of Earth's atmosphere is a non-equilibrium state maintained by the widespread diversity of life. 50% of the oxygen in our atmosphere came from cyanobacteria out in the middle of the ocean. Right? Otherwise, we use it all up and turn it into CO2, and that's not good. There's no evolutionary imperative that we have this imbalanced, non-equilibrium system. That's just the way it is. The incredible, unlikely origin and evolution of life had to be accompanied by the evolution of the Earth's atmosphere in concert with the sun's evolution. We could call it the Goldilocks syndrome. Yes. It's just right. It's not too hot, it's not too cold. Otherwise you get Mars or Venus, which is a no bueno place. Now, the implausibility of such a process has caused a scientist named Lovelock to propose his hypothesis, which is called the Gaia hypothesis. And that's all you need to know about its name. You can figure out how rational this hypothesis is. According to Lovelock, the biosphere, consisting of Earth's oceans, atmosphere, crust, and all living things, constitutes a sort of superorganism that has evolved. Life has developed in such a way that the atmosphere has been altered to protect it in the face of increasing solar luminosity. Folks, they've gone full circle and now they're pantheists. You see that?
Sounds like Eastern philosophy.
Yeah. Yeah. And born out of that, this multiculturalism. Have you noticed that? Becoming very, well, there's a reason for it. That's their worldview. Yeah, so I don't know where the sun gets its energy from, fusion or shrinking or both, but either one's kind of a problem if you want to believe the Earth is billions of years old. And you have to have a reducing atmosphere, so you have to have lots of methane up there to hold in all of this extra heat, and you have to gradually, slowly get rid of the methane over millions, billions of years at the exact same rate so that you don't get too much methane gone, everybody freezes to death, you have a giant popsicle instead of a planet. Oh my gosh, the faith required to believe this stuff, it just boggles my mind. I do not have that much faith. I don't think I ever could. But if you want to believe that, knock yourself out. Just please don't tell me that it needs to be public education and, we're going to teach this in all of our schools, but you could never question it because that would be religious, right? It's not a religious presupposition. Even if our sun is shrieking and the early faint sun paradox is not a concern, there are stars in our solar system that are much bigger than our sun. Our sun is supposed to have a 10 billion year lifespan, and it's halfway through its lifespan, right? It's middle-aged. It's going through a midlife crisis. There are stars out there that have a lifespan less than 10,000 years. Because they are so huge and they burn. Okay, we have a really big star. Why? That is a remarkable furnace you got there, sir. In fact, it will smash hydrogens together. Not just hydrogen, but also it will smash heliums together, and it will smash borons together and carbons together, and you'll get yourself all the way. You can actually build in the core of a star everything all the way up to iron. You can't get anything bigger than that, though. That's where all this other stuff comes from. Well, I'm getting ahead of myself, but they say it came from supernova explosions, supposedly generated enough pressure to build bigger stuff. I'm not convinced, but anyway. Okay, moving on to geochronographs. You could measure, or get an idea of the age of the Earth looking at the growth of coral reefs. Now, currently, coral reefs do not grow very fast, around 1 or 2 inches per year. Actually, in the since 2005, a lot of coral reefs have been kind of dying back in a process called bleaching, and it's not good. They're not doing very well. It's just kind of a bad deal for them. When they get closer to the surface has all these warm temperatures, and they really don't like that. They prefer cooler water. They get closer to the surface, and they get a lot more sediment on them. They don't like that either. They have to be able to interact with ocean water. We've been putting in these things called nuclear power plants, especially Australia and especially Japan and some of these other nations have been putting a lot of these things in, and that warms up the water around them. And you go to Australia, and right next to a nuclear power plant, there's this huge dead zone for miles. It just kills tons of reef, and when it does, that incredibly diverse ecosystem is gone. It's like a desert out there. So yeah, coral reefs have been kind of coming under fire recently, and in marine biology, one of the things that we look at is ways that we can kind of help them and try not to destroy them and stuff like that. So right now they're not doing well. They are not doing well at all. Okay, and if you had a decent media, you'd know more about it than me. I can't believe they're not talking about this stuff. The damage we're doing to our ocean and ocean life is just unbelievable. Anyway.
Global warming is going
Yeah, global warming, a bunch of nonsense. That may be part of it. If the globe is increasing in temperature, which I'm not convinced of. But let's suppose that it is happening. That's probably not helping. I think a major reason why, for example, the Great Barrier Reef has really seen a lot of bleaching and a lot of destruction in the last, say, 10 years, we've had a lot of very strong El Nino currents, and that just pumps all this warm water right directly on Australia's back door. They haven't been doing so good either. A lot of drought in Australia and California. Okay, so same type of deal. Great weather for us, though. By the way, we're about to get rid of this El Nino thing. It follows the sun cycle. We got rid of the sun cycle about 2 years back, which is one reason we had so much crazy weather then. So the sun cycle is now favoring a La Nina, and we had such a strong one. It follows in decades or 11 years, but anyway, we had such a strong one that it's finally petering out, and all the roofers are hoping that it holds out for a little bit longer until the storm season ends. And I'm just like, guys, we had a good run, right? Just relax. Give everybody a break. Jeez, if we went a whole year with no tornadoes, man, that would just, that'd be worth it. Anyway, I'll sell insulation and windows. I won't worry about roofs. All right. So currently, coral reefs not doing so well. They don't grow very fast, even on the best years, currently. But if you look at them in deeper water, cooler water, they grow anywhere from 5 to 25 times as fast as they do near the surface. And this is less well understood because it's deeper, it's harder to study it down there, okay? And it varies greatly with the amount of lime available, okay? Stony corals build their skeletons out of calcium carbonate, right? Same stuff chalk's made of, same active ingredient that's in Tums, all right? So if you have a lot of lime in the water, why these guys can grow like crazy. And it's very easy. It doesn't take a lot of energy to get all these calcium carbonate out of the water and build their skeletons. If that concentration goes down, or if the pH goes up, the more acid you have in the ocean, the harder it is for these guys to make a living, okay? And unfortunately, we have also seen the ocean's acidity levels bumping up just a little bit. And that's not good. That's not good for these guys, all right? But 4,000, 6,000 years ago, if there was a ton of water, maybe a billion tons of water, with all this calcium carbonate in it, and it erupts onto the Earth's surface, why you have a coral reef's playground out there. Okay, so it is possible in the past that the Earth's coral reefs have grown much faster than they currently do. I'm going to try to get the rest of this up. Even at the current rate, the Great Barrier Reef apparently grew in approximately 6,000 to 8,000 years. The living portion of it, okay? Even according to secular scientists, of course, there's other parts of the reef that are supposed I mean, we're assuming if we drill through the reef and we keep hitting limestone that it's all reef skeletons, I think. I don't know how you can prove that. Maybe the coral reef grows where there's lots of limestone. Yeah, you got me. But anyway, the living portion of the reef apparently grew in 6,000 to 8,000 years. Creation scientists have dated the reef even younger, at about 4,200 years. This was based on a study done after World War II. So, unfortunately, during World War II, we didn't care about the reef. We were trying to survive, especially the Australians, man. They were fighting for their lives down there. The Philippines, you know, the Philippine peoples. Man, it was brutal for them. Brutal for us, but man, it was a lot worse for them. And they ended up, you know, blowing up lots of stuff. That's war, right? Concentrate energy on your enemy to where he can't handle it anymore. And, you know, if you miss, you drop a bomb on the reef, you blow up a huge portion of the reef, which is bad for the reef. It's kind of like a forest fire, you know? You're releasing all the CO2 in the atmosphere, and the other trees are like, oh, and they just grow a lot faster, right? And apparently that's what happened to the reef. You know, we blew all these holes in it. Sorry about that. And we're kind of preoccupied here. You know, ships damaged it and crashed into it, and submarines and anchors and Lord knows what else. But it released a lot of lime into the water. And these guys grew back really quickly. And so using that growth rate, they could have got there really a lot faster. And again, this is an area of science that we don't understand very well because we don't seem to care about the ocean, which is moronic. Anyway, one of my favorite geochronographs is the recession of the moon. You guys may have known that the moon is constantly getting further away from us. We'll talk about that. The reason why the moon gets further away is because it's stealing energy from the Earth's rotation, all right, with tides. And this is easier to show you than it is to try to explain it. Okay, so you have this diagram here, all right? Now this is kind of an exaggerated diagram. In reality, the Earth is significantly larger compared to the moon than it is in this diagram, and it is much further away, right? The moon would be. You can fit all of the other planets of the solar system, of the major planets of the solar system, between here and the moon. So there's a lot of space between us, okay? And obviously the tides are on this side. But you get the idea. This is exaggerated to show detail. Okay? So, the moon is revolving around the Earth in this direction. Okay? And the Earth is also rotating in that same direction. Alright? Conservation of angular momentum. So, we're familiar with the concept of gravity. Right? Gravity is an exponential function. So, if you get yourself, if you cut the distance between yourself and an object in half, gravity is 4 times as large as it was before. If you cut the distance down by a third, or down to a third, gravity is now 9 times as strong as it was before. If you cut the distance down to a fifth, gravity is 25 times. So as you're coming in towards the Earth, why gravity is increasing a lot. But we don't experience that because we're talking about the distance from the center of the Earth to the surface. Okay, so what's that, 4,000 or 5,000 miles down there? So if we go up on top of a mountain, it changes gravity, but not much. Okay, 1 mile out of 4,000 is no big deal. You know, 200,000, that's a big deal. That's a really big deal. Okay, so anyway, so we're familiar with that concept. If you double the distance, gravity is a quarter of what it was. If you triple the distance, gravity is a ninth of what it was before. Okay, so we're familiar with all that. Now, the reason why we have tides is because the moon also exerts that same gravitational force on the Earth, right? Newton's law, every action there's an equal and opposite reaction. So the moon pulls on the Earth with the same and opposite force that the Earth pulls on the moon with. That means that since the moon is closer to this part of the ocean, it pulls on that part of the ocean with a little bit more force than it does on the center of the Earth. Makes sense? So it causes this bulge on that side of the planet. We call that bulge the tide. Now it's not much. Couple of feet. Okay, it's not this, but you get the idea. It's because of gravity. And there's also a bulge that happens on the opposite side of the planet from the moon because the moon is pulling on the center of the Earth a little bit more than it is on the ocean over there. Okay? So that's what's going on with the tides. Alright? Now, because the Earth is spinning in this direction, it pushes the ocean, this bulge, a little bit forward of an exact 90-degree angle with the moon. Does that make sense? And this is caused by friction. Friction between the ocean floor and the water, right? Does that make sense? So, because of this frictional force between the water and the shoreline, we're pushing water out ahead of the moon. This causes, since this bulge of water is here and it's a little bit ahead of the moon, this causes the moon to pick up speed a little bit, right? And if it's going faster around the Earth, it actually orbits a little bit further away. Okay? So for example, if you slow the moon down, it's coming towards the Earth, right? If you slow it down enough, it'll crash into the Earth. Does that make sense? So if you speed it up a little bit, it gets a little bit further away. Does that make sense? And it's kind of this corkscrew-like pattern. If we put a giant rocket on it and sped it up to twice its speed, it would escape the Earth's gravity and go crash into the sun or something, right? No, that'd be a bad day. Okay, so you understand the basic physics that's involved here. Okay, so if this is happening, if we are constantly speeding the moon up a little bit, that's not much, it's like 6 inches a year that it's escaping from us. Then if we work this thing backwards, all of a sudden the tide is higher, right? And it's a lot higher. If you break this distance in half, why the gravitational attraction is 4 times what it was. If you break this distance down to a third, gravity is now 9 times what it was before. Okay? And what was a small effect now becomes an extreme effect. Okay? Now you can calculate this thing backwards, and remember you have to use an exponential function, right? So as you go back in time, this effect is becoming more and more pronounced. Does that make sense? In other words, eventually these forces will kind of even out. We won't have much of a tide, and we won't have much of an acceleration of the moon, right? In a billion years or something. Okay. So back in time, this was a lot more prominent. Okay. So you get back in time a billion years ago. 1 billion years ago, you've cut this distance down to a third. So that's called the Roche limit, I think. At that point, you start to have such a great tide in the Earth's crust that you generate enough friction by that crust moving up and down, you melt the entire Earth's crust. And boil all the oceans and kill all the living things. Right? That's a no bueno. Okay, that's just a billion years ago. Okay? 1.2 billion, the Earth and the Moon would have been touching. Apparently that's what happened to all of the dinosaurs. They got mooned to death. Right? I'm sorry. I promise I'll behave. All right, I know the dinosaurs weren't supposed to have evolved yet. Don't get me started. But you understand the problem we have here, right? Unfortunately for the evolutionists, they don't really have an answer for it. We'll go over what answer they've come up with recently. But back in the 80s, they had 2 international conferences to try to figure out what the heck is going on with this thing, and they had no answer. And one old guy in the back was like, well, the best answer we can come up with is observational error. The moon does not actually exist. That was his answer. You can't make this stuff up, people. It's just too good. Okay, but you understand how this would limit the age of the Earth-Moon system, all right? Now, believe it or not, okay, so we talked about this before. The Earth's rotation always also spin, the Earth spinning faster. In the past, this increases the Coriolis effect, where you would have 1,000-mile-per-hour winds, back in time, and eroding all the mountains down to sea level, and blowing everything away. Anyway, so you get the idea here. Coriolis effect is much stronger. This is all bad. Exponential function. You can look up all the technical specs. There's a paper on it. They're linked to Dr. Walter Brown's book. All right, tides would be 8 miles high in a billion years. That's enough to cover the entire world with several miles of water twice a day. Talk about erosion. My goodness. Okay. Now, the evolutionists respond. This is almost as funny as the stuff before. They argue that the moon's acceleration was slower in the past. Now remember, we have to work with an exponential function that says that gravity, double the distance, gravity is a quarter of what it was plus, so if you work back in time, this exponential function, that's getting big in a hurry. They argue that the moon's acceleration was slower in the past. Here's what they've done. Good. Okay, so we talked about the reason why this bulge is occurring in tides and all that, or why that bulge gets pushed forward is because of friction between the Earth's crust and the ocean, right? They argue that that frictional force was significantly less in the past. Ah, well, see, if you smash all the continents together and put them up on the top of the Earth, you get almost no frictional force. So that's their response is that in the past, if you have the continents in a certain configuration, there's almost no frictional force. And unfortunately for all of the astronomy geeks over there, I hate to break it to you, pal, but most of the biologists over here insist that there were shallow oceans all over the Earth for millions and millions of years. Right? You've heard them talk, Oklahoma used to be covered with ocean, and this was all ocean, a million years ago. They are very, very adamant that there were shallow oceans all over the world, which fits perfectly with my worldview, by the way, because that's the way I would create a world if I was God. But yeah, that's their answer, is that this frictional force was way smaller, and so you don't have the moon escaping from you. And you can read about it on Hawk Origins, bring a bark bag. It's pretty ridiculous. Pretty venomous towards the creationists. So, oh my God, this is perfect explanation. It's not, it's absolute nonsense to assume that. It goes against everything that the biology's been saying for years. Okay, tree rings. The oldest living tree is 10,000 years old. I'm just going to kind of breeze through this. I want to get to ice cores. Oldest living organism. Sometimes you get more than one ring per year in dendrochronology. Very important for us to know that. Especially, okay, so tree rings are not summer, winter, summer, winter, summer, winter. They are good conditions for growth. Poor, good, poor, good, poor, good. You can have 5 of those a year in Oklahoma. So yeah, you can oftentimes generate more than one ring per year. But even assuming they're all annual rings, the oldest living tree is about 10,000 years old. And it's not even slowing down. So why don't we have a 15,000-year-old tree out there somewhere? Again, not a hard and fast way of dating the age of the Earth, but interesting. Okay, in the last few minutes here, ice cores. You go down to the South Pole, they'll try to tell you they have 135,000 years worth of annual growth rings for this ice. Again, with the dendrochronology, counting out the tree rings, this is not, they're looking at the ice and they have, wow, you have this fluffy layer of summer ice that forms, winter ice that forms when the temperature is lower, and then as the sun comes out, it melts some of the ice on top, and you get this nice, clear, denser part of the ice. And so this happens over time. You get, these annual ice layers that build up, especially if you have a lot of precipitation, like in Greenland, right? Unfortunately for them, once again, they're in a laboratory somewhere. They don't know about, weather. Temperature's always 77 degrees where they're working, or 72. Out here in the real world, this is not summer, winter, summer, winter, summer, winter. This is warm, cold, warm, cold, warm, cold. And Oklahomans will all tell you, you can have 50 of those in about a month. Right? Absolutely. There was a guy in Alaska who took a picture of the ice and snow buildup on his car, and he had 15 layers that formed in an hour. We think our weather's bad. I would not want to live there. Okay. Yeah, that's absolutely ridiculous. We have lots and lots of evidence that these layers form very quickly. As a matter of fact, we found some airplanes from World War II way down deep in this ice. They got stuck in there in 43 or 44, I forget which, but they had like 1,200 years of ice work on top of them. Obviously, these layers are forming very quickly and very widely as precipitation varies. Right, so in Greenland, you got all kinds of layers that are forming, not so much in the last 20 years, but you know, in World War II to 2000, when they dug up those plains, they had a lot of ice that formed over there, the little ice age and all that nonsense. You get down to Antarctica, it's kind of a barren desert, less than 2 inches of rain, snow per year. You get you have a very thick, lots of ice layers. The question is, has that precipitation rate remained constant over, the last 10, 20, 30,000 years? I don't think so. I think you could have easily had a very much higher rate of precipitation, especially right after the flood. You have really warm oceans, you have really cold continents, lots of volcanic ash in the atmosphere, a very cold atmosphere. You're going to have yourself precipitation like nobody's business.
Especially with the dimmer sun.
Yeah, with a dimmer sun. Yeah, okay, so, and also they did not count all these layers, okay? They're counting this much, and they're counting this, and they're averaging, and they're trying to calculate up how much ice is out there, okay? And I shouldn't even mention this, but you can't even count them in the lower portion, okay? Because they're all squished together. So you're really taking some liberties with your numbers and trying to make sure that you know how much is this going to compress and things of that nature. So yeah, that's all I've got to say about the age of the Earth until we get to astrophysics. Questions? You can understand why somebody like me would kind of laugh when we get radioisotopic counting dates running around. I don't consider them to be very valid.
Why do they continue doing it if it's so unscientific?
It's all they got. It's like Archaeopteryx.
They need a job. It feels
They did a real job in the real world, but they actually made something useful.
Yeah.
The problem is that if they don't believe what they come up with, then they have to believe what we believe.
There you go.
Yeah, and
Yeah.
they look like idiots all these years.
I told you the story about the was it paleontologist or was it geologist, but they came out of this big conference and they all decided, okay, we have to actually admit that uniformitarianism isn't true because we have all this evidence that fossils form rapidly and all this stuff. And so they came out and they all decided they were going to admit it, and that's what they believe today. And one of the older gentlemen said, well, I'm just terrified, guys, that we're going to climb this giant mountain of knowledge in our pursuit of science. We're going to get to the very top and find out the Christians have been there the whole time. And that's kind of the way I feel about it, yeah, the implications of the worldview, all the...
Well, wouldn't that be scary for them?
I would be terrifying. They've been teaching their students that this is the truth
Yeah.
for decades.
Yeah.
So
That
Satan's pocket.
that World War II plane, isn't that where they got Captain America from? Underneath the ice?
that could be true. They got them out of there in the Tesseract, I think, as well.
Yeah.
That's wrong.
Shall I punch your nerd card for you?
That's wrong. Well, only a nerd can punch a nerd card.
Takes one to know one. I know it.
That's right.
I'll admit it.
What'd you say, Becky?